Okay, thank you so much for the kind introduction, and thanks the organizers for inviting me. I'm very humbled and honored to be here. As I told a few people, I've been living in New York City for 14 years, and this is my first time in Roosevelt Island, and it's beautiful. I love it. Um, so today I'm going to talk to you a little bit about some of the work that we've done that was motivated by needs that come from AutoML and using AutoML in practice. And of course, this is a work from a number of different people in my group and collaborators. Okay, I have too many messages here. Okay. So maybe I don't need to convince this audience that from scientific discoveries to improvements in healthcare and a lot of money being made, machine learning and AI have actually revolutionized our work. But the realization that we have is that machine learning, using and applying that in practice is very, very hard, right? And AutoML and this community has made great contributions in that, AutoML now has emerged as a very effective approach to automate many of the very tedious and time-consuming tasks that you have to perform in machine learning, right? So it's kind of like this vision of having machine learning for all. And it has had a lot of success. It does make data scientists and experts more efficient. They enables people to actually work on harder problems and be faster. And it does democratize machine learning to a certain extent in the sense that, it is possible for some domain experts to actually build these models on their own. Right? But there are a number of remaining gaps. The first one is the diversity problem, right? While organizations use machine learning, they use it for many different problems, classification, regression, multi-class, binary, clustering, and so on, right? So instead of having a million tools that support each of these problems, what if we could actually have a general solution that supports these heterogeneous problems as well as different kinds of data types, right? The other problem is, that while automation sounds great in practice, AutoML actually augment users. So we really need to design systems that support human-in-the-loop workflows. So I'm going to be talking about some of the work that we've done that helps experts or machine learning experts to actually visually explore and obtain insights from pipelines that are generated from AutoML. And finally, in machine learning, people, in particular in vision and object detection and so on, people have relied heavily on data augmentation to build and improve models, right? When we're dealing with structured data, there are already lots of data sets out there. So one important question that we ask in our research is, can we actually leverage this structured data? Can we discover this data and augment our training data to improve models? And I'll be talking about some of the work that we've been doing in rethinking data set search. So because AutoML, can mean many different things for different people, just to set for the remainder of the talk, I'm going to be focusing on AutoML systems and techniques that actually support the construction of end-to-end pipelines. Given data, a task, some time constraints, you have an AutoML system that is going to orchestrate these primitives to build an end-to-end pipeline, right? So the first problem that we looked at, and that was motivated by a DARPA project, the D3M program, was, how can we build general AutoML systems that can actually handle a multitude of tasks and data types, and problems like regression, binary classification, object detection, and not only tables, but images, text, sound, and so on. Right? And the big challenge that we have when we try to support all these different problems and data sets is that, there's too many combinations of primitives that you end up with. And it can be very expensive to construct and test a very large number of pipelines. Just to give you an idea, we use these D3M ecosystems, which had 312 primitives, and over 1,500 parameters. So if we want to search just for one particular problem, which is classification over tabular data, there are 22 data cleaning primitives, 87 data transformations, and 44 classifiers. So if we actually look at all the different combinations, there are over 84,000 pipelines to construct and test. Right. So our approach to this was to actually design a reinforcement learning based system that learns how to synthesize pipelines, right? And the inspiration for that comes from AlphaZero. And the analogy is that, analogous to the board configuration or the state, we have the pipeline, the current state of the pipeline, and the data it's processing. And then the actions that you apply to each state are adding, modifying, or removing some primitive or a node in the graph. Right? And the way that this works is that in an iterative procedure, neural network in combination with Monte Carlo tree search is used to select the pipeline structure. So the pipeline structure is incrementally constructed, and it predicts the performance as well as the probabilities for the next action to take. Right? One of the challenges is that, yes, this actually worked in practice, but it learned very, very, very slowly. So our solution to that was to actually use a grammar to try and constrain the search space. And that worked well, but the grammars that we built were necessarily limited and didn't cover all the cases. So we actually also did some work on using meta-learning to automatically construct grammars, and this actually led to huge improvements in the quality of the derived pipelines and their performance also. Right. The system that we built is called AlphaD3M. It provides, it implements this search procedure that I just described. It iterates over a set of primitives, and it also uses a meta-learning database that consists of a number of pipelines that have been tried and used in the past. And it has an API that is exposed through Python that enables users to define problems, to explore data, and it outputs model summaries and also supports model exploration. Right, so with just a few lines of code, you can actually create a model or ask the system to generate pipelines. Right? And one of the big advantages of AlphaD3M is this task coverage. While most of AutoML systems support a few tasks, most of them support tabular classification and regression, AlphaD3M actually supports, all these different, the 17 different tasks. And even though it's general, we actually compared it against other AutoML systems using the OpenML benchmark. And even though the system is general, when you compare with the systems that are specific, AlphaD3M actually has performance that is comparable to these more specialized systems. And you may actually look in quickly at these numbers. Our system is the blue one. You can see that in some cases it performs really badly. But the reason that it performed badly for that particular case was that we are missing one primitive that was critical for this particular problem. Right? But overall, what we learned and shown is that, this ability to learn how to build pipelines is actually, very powerful and enables the creation of these general pipelines, as well as, the ability to integrate new novel primitives. Right? But this project, this DARPA project ended, and, we started to look at some of the limitations of AlphaD3M, right? And one of them was performance. Yes, it's effective, but it still took a long time to generate the pipelines. So we explored and developed different alternatives to predict performance as well as to hopefully improve the learning. And this is where we actually replaced our, original architecture with PPO. And that actually led to much faster learning rates, as well as better pipelines than what AlphaD3M used to derive. And the other thing that we changed in AlphaAutoML is that AlphaD3M was limited to the primitives that were available in the D3M collection. And we extended the system so that we can integrate new primitives on the fly. And we currently have wrappers for Hugging Face, PyTorch, and FastText. So this actually enables you to automatically discover and integrate these primitives on the pipeline on the fly, right? Um, and we ran some preliminary experimental evaluation, and Alpha AutoML actually is more efficient than Alpha D3M, and it's in the top when compared to other popular AutoML systems, right? So this is kind of like a how to tell you more, like to give you some context of how I got into this area. But one thing that we clearly noticed, and I work in an interdisciplinary group, the VIDA Center, Visualization, Image, and Data Analysis Center at NYU, and we have a lot of people that work on HCI and visualization. So the first thing that we kind of like realized is that just having the automation is not enough. It's great that a system like Alpha AutoML generates all these different pipelines, and it does that automatically, right? And yes, it says the F1 score, so maybe we can actually blindly select the one that has the best score. But in reality, and we've seen that many times in practice, sometimes the best performing pipelines is just overfitting and predicting the same value for all input points. Right. So we do need to have better ways to evaluate and compare pipelines, not just consider efficiency, but also the correctness and faithfulness to what you want the model to do for your specific application, right? And we also need to help users obtain insights on how they can customize and improve their pipelines or improve the data, right? Augment the data that they use to train their models. And very importantly, how can they assess the correctness of these pipelines? Are they robust? Are they correct, right? And we pursued two different directions in this work. One was a system that we built to support domain experts through the whole process, from specifying the problem, finding the data, exploring the data, bringing the data together, using AutoML to do the model search, and then enabling the user to explore these pipelines and make informed decisions of what pipeline is actually the best for their particular task. The other project that we worked on was more focused on machine learning developers, and we developed a system called Pipeline Profiler that aims to provide the ability or empower the machine learning experts to explore all these pipelines and obtain insights. And I'll give you more specific requirements that we considered, right? So one of the big motivations for the pipeline profiler was actually we saw in the D3M project, and was actually discussed in a survey, in a study that was published in CHI 2021, where they found that the lack of transparency is one of the key concerns of people that actually use AutoML. And this demands that we provide the users with the ability to understand and build trust in those results that are automatically generated, right? So to develop Pipeline Profiler, we actually focused on two key requirements. One of them came directly from the D3M project, and what D3M, DARPA D3M aim to do is we build these automated AutoML systems. And there are over 20 groups building different systems to support AutoML. And one big challenge that people had is, how can you actually compare these different systems beyond just the performance numbers for the pipelines they derive? And the other one is that, I have my system and it produces a number of pipelines. How can I get insights into, whether these pipelines are useful, how good they are, and also how can I actually improve my AutoML system to generate better pipelines, right? And what we observed in this big group is that developers were just staring at text that describe these different pipelines and struggling to understand the pipelines and how and if and how they actually worked. right? So Pipeline Profiler aims to address these challenges and enable the visual comparison and exploration of, AutoML pipelines. So I'll just briefly go through, what the system does, how it actually works. So it can be used within a Jupyter notebook. So, as you build your results, and then you can just upload the pipelines that are derived within your Jupyter notebook. And it has two different components. It has the pipeline matrix, and it has a pipeline comparison view. Each row in this matrix corresponds to a pipeline, and each column corresponds to a primitive, right? For example, modeling primitives or data processing primitives and so on. Right. And on the right side, we actually have the pipeline scores, and we can also show, say, the running times for the models. Right. The system also displays what we call the primitive contribution. And this actually is an estimate of the contribution, that is computed using Pearson correlation between the primitive usage and the pipeline scores. Right? So for example, deep feature synthesis here is highly correlated with, and it's present and used in pipelines that have good performance or high performance. While in contrast, random forest, whenever it's used, the pipelines have really poor performance. Right, and we also display to show the hyperparameters. We use a one-hot encoded matrix representation, and then when users select different primitives, the hyperparameters for those primitives are actually displayed here. Right, and in the bottom here, users can select different pipelines. So here I'm selecting 3 different pipelines, 1, 2, and 3. And in the pipeline comparison view, you can see a visual difference of the selected pipelines. So the primitives that are shown just like with the black outline are the ones that are repeated across the different pipelines. And we use color to show the primitives that are used by specific pipelines. So for example, data set map is used only by the 3rd pipeline, while, and I cannot read this, the loopy resell is used by the orange pipeline and so on. So that gives like the user a good overview and some clearer idea of what these pipelines are actually doing and what primitives they're using, right? So we deployed this within the D3M project, and the feedback was that the tool was actually very useful, and they used the tool. They found the tool useful for a number of different tasks. One is to find useful primitives, maybe primitives that other people are using but were not using in their own AutoML system. They identified bugs in primitives. For example, looking at primitives that always gave incorrect results. Right? It was useful to compare parameter search strategies across different systems, as well as to try and understand how the underlying search actually works in the different AutoML systems. Right. So I'll go through a few use cases that were shared by these users. So one of them was working with this Libras move classification data set, and the expert was analyzing the pipelines, which is a multi-class for multi-class classification, where the goal is to classify hand gestures for Brazilian Sign Language, right? And this particular developer was concerned because his pipeline was, performing really badly, while a number of the other systems had accuracy of over 80%, right? So he noticed, analyzing the other pipelines, that feature selection primitives shown here have a big impact in the classification problem, right? So pipelines with the feature selection performed a lot better than pipelines without the feature selection. So he used this insight to extend his AutoML and included this particular feature, and the performance of his system actually improved from 79 to 88. Another application that I mentioned is this ability to get insights into how the search strategies of different AutoML systems, how they work. And for this particular problem, CPS wage regression, the user was comparing the search strategies by examining pipelines derived by different systems. And for one of the systems, what he noticed is that the system actually used a fixed template, right, which has all these, the black outlines here. And the only thing that the system was actually trying and exploring was the estimator step, right? And then for another system that he explored, he noticed that there's also a template that always uses XGBoost. And what the system explores is different strategies for pre-processing. So you can easily see that this is much better than looking at textual data that describes structured, DAG-structured pipelines, right? And the last example that I have was something that we experienced ourselves in our group, and we were working on this problem where we had to identify events described in text that actually involved terrorist activities. And in particular, whether the text indicated something about explosions, right? And we used alpha G3M to generate pipelines, and it actually got a really good F1 score of 0.91. The problem was that the execution time was pretty bad, was about 14 minutes. But exploring, looking at the different pipelines using Pipeline Profiler, what we saw is that there are other pipelines that have similar performance, but have a much lower running time. So that gives us the insight, can we actually improve our pipeline so that it keeps the high F score, but decreases the runtime. So what we did, and this is one example of the human in the loop, we implemented a new method that actually does progressive sampling and reduces the size of the training data set. And by integrating this new primitive, we got the execution time reduced significantly from 800 to 100 seconds. And also, the best performing pipeline ended up having a higher F measure of 96, right? So I think that these examples kind of like give you some evidence that being able to explore these results and understand the pipelines that are output by AutoML has a lot of promise. And having the human in the loop is actually crucial to derive models that are not only have good numbers, but actually are good and working practice. Okay, any questions so far? Okay.
Is there something about the evaluation cost?
Sorry?
The evaluation cost is pretty high, right? Like in a practical scenario, how would you envision this to be? Sorry, I will repeat my question just for people online. So I was saying that to evaluate all of these is quite costly, right? So you need to, quite some compute in order to derive these. So for you, what would be a typical scenario where you would apply such kind of analysis? And
so in terms of Pipeline Profiler, right, it is just displaying results produced by AutoML, right? So the cost and how to actually schedule and efficiently execute these are kind of like orthogonal. For G3M, we did have a dedicated cloud infrastructure that enabled us to do these searches and build all these pipelines. But most of the times, we set the running time for the AutoML systems, I think it was 1 hour. It was not such a big problem, but we're not looking at LLMs, right? So this is more like traditional machine learning.
Yeah.
So if you have to do these more expensive ones and neural networks and so on, it would be hard to generate all these pipelines, right? But I think that that's more of a challenge for the AutoML community.
Okay, great. And could you say a few words about how you, I know this is not the profiler part, but more the search part, let's say, how you build the pipelines? Is there a structured way of building different pipelines, or this is just up to the user? And
No, so what do you mean?
like those pipelines that you compare here,
Oh, so these are built, so all of these.
They are manually built, or
No,
is
no,
there a
no. So
system
these,
behind that you would like?
so these are built by different AutoML systems,
Okay.
right? So these are all outputs. So here is like system A produce pipeline one. This is pipeline one of system B and so on, right? So these are all automatically generated pipelines.
Okay.
Right? But, you could also use this potentially to compare manually built pipelines.
So you don't search essentially over the pipeline space. No, this is out of
No,
scope
so
here.
this is
Okay, it's
so
really just profiling. I mean, just in
it's just profiling,
just
right?
profiling.
You
Okay.
have AutoML, they generate lots of pipelines. We provide a way of exploring those pipelines.
Okay.
Okay.
Thank you.
Okay. Okay. All right. So the other challenge that, or the other opportunity that we identified working, on this project, was the fact that there's a limit on of where AutoML can get you in terms of optimizing the primitives and pre-processing and so on. And there's a lot of opportunity to use the troves of data that are available in open data portals, scientific data repositories, as well as in enterprise data lakes, to actually improve the data, augment the data, and that can actually give very high, big improvements in the quality of your models, right? But then there is that's where we found the big challenge, right? The first one is that, the data sets are available, but they're very hard to find. They're spread over multiple sites, different repositories, data lakes, right? So it's hard to actually, figure out where to go for the data sets. But this is a problem that has been already addressed by some of these repositories, in that they try to combine and organize the data sets, specifically the metadata of the data sets, and serve this metadata in a centralized repository with a search interface, right? And we see a number of different systems that already do that. You have open government data, like, for example, NYC Open Data. There is repositories for scientific data sets like Harvard Dataverse that collects data sets for papers in social sciences. And there's also Google Dataset Search, which is a generic dataset search engine that actually piggybacks on Google Crawler. And as the Google crawler is going to find new web pages, if it encounters a schema.org description of a data set, it will actually index that in Google Dataset Search, right? So you have examples of verticals as well as more general dataset systems. And they're effective at kind of like indexing and providing you a unified access to data sets that are that come from different data sources, right? And what these systems do, it's very simple to traditional search engines. You can input keyword queries, and they return textual snippets that kind of like describe the data set, like has a data set name and some brief description, right? So essentially what these systems do is do for data sets what search engines do for documents. So essentially what they treat data sets or view data sets as a document that contains metadata about the data set, right? But it's challenging when you have these very terse descriptions to actually assess what data set is relevant or not, what data set answer your information need. And these snippets or these data set descriptions can be very uninformative. So here's a real example. The city bike system data here in New York City is described as data to solve city bike's big idea. So good luck finding this data set. The only thing that you can do is actually download the data and actually look at the contents to see whether it actually has the attributes that you need, say, to improve your model. And it gets even worse because, not only the metadata is necessarily incomplete, it can also be inconsistent with the data. So one example that we found in NYC Open Data is that there's this data set called 2018 Yellow Taxi Trip Data. But if you actually look at the contents of the data, there's also trips for other years, for example, 2020. So if you're searching for 2020 taxi data, you're not going to find this data set, right? So what we've seen and other people also is that there is this huge mismatch between what users need from these data sets and the metadata and search capabilities that are actually available by these data set search engines, right? And they collide. And right now, we are back to the early, for data sets, we are back to the early days of the web. Remember that they had directories? So you go to a directory and you find, oh, this is the link, I should go to that particular website, right? So for data sets, we're living this reality today. And if you know what you're searching for, you have a chance of finding that. But, really discovering something that you know about is really hard, right? So I'm not going to comment on this, but for the older people of you, you're probably going to get this. This is Donald Rumsfeld, and he has this whole thing about discovering unknown unknowns. So that's what we're doing. We're trying to do what Rumsfeld talked about. So we set out to actually rethink how we can better do data set search and support data discovery. And we started building this new data set discovery and augmentation engine that we call Octus, right? And Octus is different in the sense that it's like these other systems that tries to put together data sets from different sources, but it actually relies on different methods to actually discover these data on the web. So we've developed crawlers that are specialized at finding data sets that are spread over the web. And the system is also able to ingest data sets from different repositories, from Zenodo, from open data portals, scientific repositories, and so on. And a key differentiator of Octus is that it does not rely just on the metadata that is provided by the data publishers. It leverages the dataset contents to derive richer metadata that can improve findability. And we index this metadata and allow users as well as systems or agents to search through the data through a rich query interface. And I'm going to tell you a little bit about some of the queries that we support that were designed to support diverse information needs. Right. We also, again, coming from VIDA, we actually explored new visual representations and interaction modes. Right. So I'll tell you a little bit about some of the strategies that we use for this. So I talked about the inadequate data metadata, but just to give you some numbers, in Octus, 13% of the data sets have no description whatsoever. And about 10% have descriptions containing less than 10 words, right? So clearly, these data sets, even though they're there, they're, effectively invisible, right? And what we need is to have ways that answer or to discover the data sets by answering questions that the users want to know about these different data sets, like what the data set is about, what is its topic, what are the value types, value ranges, time span, spatial coverage, and so on. Right? So the recent work that we have done is using data as well as augmenting that with knowledge from LLMs to automatically generate data set descriptions, right? So we leverage the LLM to produce this fluent, readable text that can help users assess the relevance of the data set, right? That also are aligned to the user information needs, that are faithful to the data and accurately describe the data set contents, and they're also concise and readable to facilitate quick assessment. And the framework we built is called AutoDDG, and it combines algorithmic profilers that will produce global statistical summaries of the individual data sets, and combine that with LLMs to uncover the semantics of the data set, what the different attributes mean, what the topic of the data set are, right? So this is an example of a kind of like a framework that instead of using just an LLM as a black box, you build the whole architecture and you place LLM in key places that, produce an effective result, right? And here one clear challenge is scalability. If you have, say, NYC Open Data has 2,500 data sets. If you try to use LLMs to describe each of these data sets, it's going to be very expensive. So one important feature of this approach is that by using algorithmic profiling and generating these global statistics, we can actually have a much better idea of the data, and we can parallelize that using the algorithmic profilers. And we send to the LLM just a small description that has the key features of those data sets, right? Because of that, we summarize the data. We don't need to sample, which would actually lead us to miss potentially important features of the data sets. As I said, the summaries can be efficiently processed by LLMs. Having this data-driven process also creates some guardrails for the LLM and avoids or reduces the risk of hallucinations. And we also shown that the framework is general and it can be customized for different information needs. So for example, in our paper that is in archive, we actually show that the system is effective to generate descriptions that are user-focused and help with user assessment, as well as search-focused descriptions that actually improve findability and retrieval. Okay. So we ran a number of detailed experimental evaluation of the system, and we did show that using these automatically derived descriptions significantly improves the recall and the data set findability, going from original descriptions that had NDCG of 66 to using our method 84. These descriptions are also high quality, and for this evaluation, we actually used LLMs to assess whether they're similar to a gold standard. The results were very positive and showed that the descriptions are both accurate and of high quality. Right? So this is one way that you can actually improve findability. But sometimes you have specific information needs. And here, this community, a common information need is you have your training data, you're building your model. Like in this case, we are trying to predict taxi demand. We have historic taxi data that has pickup time, a location, and the number of trips in that particular location and time. And you'd like to predict taxi demand. So we can use random forest regressor, but the error can be very high. And the question is, can we find additional features or additional data sets that can be used to augment this data and improve the model? Right? And right now, these days, what people usually do is they have some intuition and they can search for the data set, right? And the techniques that we develop can help at that. So in this case, the person doing the taxi prediction knows that weather definitely affects taxi demand. So they can go, say, to Google and look for New York City weather, sorry. They find a Kaggle data set. They can join the two data sets. And now they retrain their model, and boom, you have a big improvement. Now you have a 41% improvement and a much lower error, right? The problem is that there's lots of data sets out there. So just NYC weather in Google returns 34 data sets. And the question is, which ones can be merged with your training data, and which ones will actually improve the model, right? Right now, to search for data, you have to be hypothesis driven. You need to use your intuition and actually know where to look for these data sets. Right? Yes, you can, you found these 34 data sets, and you can use a brute force to check which data sets are going to be useful. So you have your taxi trips, you have your data lake, you have your 34 data sets that you found that might be related. You can try to join them. And the ones that you can actually join with your data, you can augment the data, and you can retrain the model and test whether there's any improvement, right? The problem is that this is very expensive and it's not feasible for large collections. And the question that we asked is, can we efficiently find variables that help predict a target variable in large-scale data collections, right? And this is what motivated us to propose this new discovery query, which we call joint correlation queries. And it provides this data-driven approach to discover unknown unknowns, data sets that you didn't know about, but that can actually improve your model, right? So the idea is that you have your taxi data, and using correlation joins, you're going to find not just the weather indicators that you had your intuition for, but you're going to find other data sets that, because they're correlated, might affect the output of your model. And since I'm running over time, let me just quick through. So, this is a formal definition of the problem. We'd like to find data sets that are joinable and that have a variable that is correlated with your target variable. And the challenge here is that we have this, big data lake. And in order to find the correlation, we actually need to join the data sets and, compute the correlation after you join these data sets. And this is very expensive, as I illustrated. So our idea was, can we actually reduce the input and estimate these correlations, right? And derive approximate results, but derive them fast. And our challenge was, how can we estimate the post-join correlation of these independent tables? So this is not trivial, because if you just sample values for columns or you sample rows, this is not going to work, because to compute the correlation, you have to align the values by the join key, right? So we proposed this new type of sketch, which we call correlation sketches, that is an extension of KMVs. And it uses a hash function that creates a compact randomized sketch for each data set, but it does so in a coordinated way. And what we showed is that given two independently created sketches, we can recover a uniform random sample of the join of the original tables without having to compute the full join. And once we have that, we can actually compute any kind of correlation estimator over that, right? And maybe I can go fast over these. So when we have the sketches, we can index them using an inverted index. And with that, we can support very fast retrieval for joinable tables. So essentially, we're searching for tables that join with your query data set that have a high overlap on the hash keys. Once we find them, we compute the join of the sketches, and we compute the correlation over the join sketch, right? And we've shown that, this actually leads to a system that has search that is very fast, so you can find correlated data sets in big, large repositories with sub-second response times. We also shown that, you can obtain large, accurate estimates. And of course, this is not perfect, but we proved error bounds, and we actually use those error bounds to rank the results so that we avoid bad tables or relations to be returned up in the ranking, right? And what this shows is that there's actually the potential to improve machine learning models by discovering data that you did not know existed, right? So let me try to just close with some general notes. And I think that, AutoML has gone a long way, and it has democratized ML, but to a certain extent. And but what we see is that it's still hard for domain experts, and it's also still hard for even experts to actually make good use or more effective use of these systems. So we do need to think more about how to best integrate the user in this, automated workflow. Of course, with LLMs and agents, we also have a lot of opportunity to actually improve this usability, right? We can now allow people to specify problems in natural language, and in the co-pilot way, also to discover and suggest new primitives that can be used to improve your machine learning pipeline, right? And data set discovery for augmenting structured data is promising, but it also brings new challenges, because, to combine these different data sets, and I was talking about that to Jan before, is that it's really hard, right? So AutoML is, focuses on this small part of the data engineering pipeline. So you have all the data discovery, data cleaning, data integration that takes an absurd amount of time before you can actually do any machine learning. Right. So recently, we actually been working on new methods and tools to streamline this process of integrating data from different sources. So at NYU, we've built this new library called BDI Kit that combines state-of-the-art methods that perform common tasks for data integration, including schema matching and value matching and matching evaluation. And we've also been developing new primitives that support these tasks that actually make use of LLMs and AI. Using this library, we can actually build these workflows, these pipelines that do the data integration or harmonization. You read files, you match schemas, you map values, and you generate the integrated data set, right? But just like ML pipelines, this is hard to build. So we've also been working on, on new ways of actually inserting or helping the users in this very challenging task. So data scientists can use the library directly using Jupyter and Python. But we've also developed a number of different new interfaces that empower domain experts to actually perform data integration themselves. We built this agent-based system called Harmonia that provide this chat-based interface, and users can, using natural language, build these integration pipelines. We've recently also enabled the use of Claude for the same purpose. And we are building also visual interfaces that help users both explore and curate the results of these automated techniques for data integration, right? And I see a big opportunity here that I've been in terms of actually whether we can apply some of the AutoML ideas to create these data integration pipelines, right? So I think that the agents go a long way, but they do kind of like an open-ended search. So what I envision and what I'd like to try is, can we actually combine these agent-based interfaces with the more systematic exploration that AutoML provides to help us build high quality and high performing data integration pipelines. And one of the big challenges that we have here is that unlike machine learning methods and models for which you have these, very well-defined metrics to see, oh, this is better than that. For data cleaning and integration, this is a big open problem. I apply one cleaning technique and another, and I look at the results, which one is best? And this is very difficult to assess, right? Finally, to close, automation is not enough. We need explainability, trust, and the ability to debug these pipelines, right? And this is an area that, regardless if it's manually created by an agent or an AutoML system, we need to build trust and understand how this pipeline works. So I think that there's a lot of space for us to actually work on maybe AI augmented techniques to help users find bugs in their pipelines. With that, I thank you all, and I'd be happy to answer any questions.